Hi, welcome back to our first example. We'll get this one started. It's just an example of doing a vertical and horizontal stretch and compression. So we're going to see all four scenarios that we can have. Given this function, this will be our base function that we'll be using for all of these. We're going to write equations to represent g of x. Those are going to be the new ones, g of x and h of x. And then we'll just describe the transformations. Once we're done that, we're going to take our base function and we're going to transform it to get the sketches of g of x and h of x, and then state their domain and range. Okay, let's begin. We'll do this one in blue, and then we'll do this one after in red. So there's not a lot of room on your paper, so just be a little bit careful to kind of conserve space. So here we go with part A. We're told that g of x is going to be the new transformed function. So it says to just take f of x and multiply it by 2. So when we multiply a function by 2, we're actually going to be multiplying its output by 2. So it's going to become vertically stretched. So anyway, our equation is going to look like 2 times, and then we just write in whatever f of x is. F of x is root x, so we just have 2 times root x. That's our function g of x, okay? I can see from this function that a is equal to 2. Okay, that's our number in front. That's our parameter, 2. So if a is 2, according to our definitions, if a is greater than 1, then we have a vertical stretch. So, and a is 2 in this case. So we actually can say since a equals 2, that'd be a little bit better. Since a equals 2, the function okay, is vertically stretched by factor 2. So our factor is always the a value. So we're going to put in factor 2. Okay, what this means is that our points x, y for the base function, they're going to turn into x comma 2y. Okay, that's how we're going to get all the new points for that. Okay, before we start graphing, we're going to work on h of x, and we'll get that one ready. So h of x is equal to a half times f of x. So it just says take the function f of x and multiply it by a half. So f of x is root x, so we have a half times root x. And it's properly written this way, root x over 2, right? Once you do the multiplication, and you imagine there's a 1 underneath, 1 times root x, and then 2 times the 1. So this is h of x. All right, and we can tell by looking up here, we can see that a is a half. So we can say since a equals a half, the function is vertically compressed by factor 1 over 2. Okay, remember if you're using the word compressed or compression, your factor should be small, between 0 and 1. What this means is that my points x, y are going to turn into x comma a half y. Okay. All right, let's get our base function set up. So we're gonna get our famous table of values for root x. So you've probably done this so many times now that you're starting to remember these key points. So those key points are now gonna map over to get us new ones. So we'll do g of x first. So this is gonna map over to x comma 2y, because that's a vertical stretch by a factor of 2. So our x values will be untouched, but the y values get multiplied by 2. So I'm going to take these here and I'm just going to multiply them by 2, like we can see there. So 0 times 2 is still 0. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. So those are those new points. To get h of x, we're going to take the base ones and we're going to map them over to this formula here. Because it's compressed vertically by a half, our y values get divided by 2. So it's like we multiply y by a half, right, to get y over 2. X values stay untouched again, and the y values, we're just going to take these from the base function, and we're going to plug them into y right here. So 0 over 2 is 0. 1 over 2 is a half. So you can write it as a half. You can write it as 0.5. Both are okay. We're just using these to get a graph. 2 over 2 is 1, and 3 over 2 is 1.5. So those are all my ordered pairs. Time to set up my axes. So x is positive for all of this, so I'll just set up the y-axis over here. Okay, I kind of screwed that up a little bit there. Let's just go over top of it. Okay, that's better. So there's our y-axis, and then the x-axis. Looks like all our y values are positive, so I'll just show the y-axis over here. Sorry, the x-axis over there. And I'll make it a little bit thicker like the other one. Okay. All right, let's plot our points for the base function. So we got one at the origin. Can't really see that, but there's a point there. And then we got one at 1, 1, 4, 2, 9, 3. Those are our points for f of x. Okay, g of x, the one in blue, that's vertically stretched. All the y values get multiplied by 2. Okay, so you can either plot these, or you can actually multiply the y value. So this has a distance of 3, right? It's a distance of 3. Well, if I multiply that by 2, I end up getting a distance of 6 to the new point. So I actually just kind of take these y values and then I double them to get the new points. Even this distance kind of gets repeated over here, right? Okay, so that is g of x. All right, and then we'll do our horizontal compression. This is for h of x. Should write the h of x down there above it. We got 0, 0. It's 1 point. We got 1/2. So that's right here. And we got 4, 1. That's right here. And then we got 9, 1.5. That'll be right here. So you can see all the y values were cut in half. Okay, so this distance of 3 is now only a distance of 1.5. This distance of 2 is now only a distance of 1. Okay, so it's like we apply a scale factor to our distance from the x-axis. So whatever our distance is from the x-axis, we take that and we multiply that by a scale factor. So if a is 2, it doubles, and we get this. If a is small, then it shrinks, and then we get this. Okay, so that is our first example A, showing what happens if A is greater than 1, and what happens if A is between 0 and 1. Okay. Now you might be wondering, what happens if A is like negative? What if we have like -2 or something? Well, remember when we did the reflections tie in with the negative value. Okay. So when we do any of these questions, we look at the value of A, and I believe in your homework, all of them are going to be positive. But if you do see a -1, then it just means you can ignore the negative, and you'll have to do a reflection and a vertical stretch or compression. All right, let's do this one here. B, we have green, and we'll do green for g of x, orange for h of x. So we're told g of x this time is equal to f of 2x, okay? Notice the parameter is inside the function. That means this is our value of k. So we know that k is going to be 2 in this case. Let's go ahead and calculate the equation. So our base function is still root x, so we're supposed to switch x with 2x when we plug it in. So we get root 2x. Okay, that's g of x. Okay, notice to get the same output as this, we're going to have to put values of x that are half the size in. That's how I know that this is going to be a compression. Okay, so when I plug in 1 for x, I end up with 2 before I square root it. So plugging in 1 is the same thing as plugging in 2 for this one. That's how I know that this is going to be a horizontal compression. Okay. So there's the equation. Okay, we could say since k is equal to 2, the function f of x is horizontally, and it's not stretched, it's compressed by factor. And according to the definition, we're supposed to do 1 over k. So my k is 2, so I'm going to have 1 over 2. That's my scale factor. And remember, if you're multiplying by something small, like a half, it's going to get smaller, it's going to get compressed. Okay, so that's the proper kind of lingo that you need to have. If you're using the word compressed, your factor better be less than 1. Okay, that's true with the vertical stretches and compressions. Notice we had a is a half, and we said vertically compressed. If a is greater than 1, then we should use vertically stretched. Okay? With the horizontal stuff, our factor is always 1 over k. That's by definition. So our factor, if it's a half, then we know it's horizontally compressed. Let's do the next one. H of x. H of x was equal to f of a half x. A half times x. Yeah. So that means I got to replace x with a half x. So I'm going to have the square root of 1/2 times x. Okay, you can leave this like this, or you can kind of clean this up and you can write it as x over 2. Okay, if you're going to write it as x over 2, make sure this whole thing is underneath the root. Not just the x, but also the 2 in the denominator. So that is h of x. We can say, as far as our transformations go, since k equals a half this time, the function is horizontally stretched by a factor. The factor is always 1 over k. And this time our k is a half. So 1 over a half is actually going to be 2. So I'm going to write this 2 here. Remember, the factor is always 1 over k. So if k is a half, we have 1 divided by a half, right? To divide, you have to flip and multiply, so you get 1 times 2 over 1, which is 2. So that's how I arrived at this value of 2. Also, I know it's horizontally stretched by a factor of 2 because we're multiplying the x by a half, I have to put in values of x that are twice as big in order to get the same thing as my base function. So if I'm putting in x values that are twice as big, the points are going to move from one spot and they're going to get bigger and they're going to move over here. That's why we say it's horizontally stretched. Okay, let's get some order pairs. So we're going to take our base function and our x and y values, 0, 1, 4, 9. Those have 0, 1, 2, 3. We're going to get the green graph first. So those are going to map over to g of x. This time, it's my x values that are changing, right? So if this is a horizontal compression by a half, that means I'm multiplying the x values by a half. So I can write x over 2. And then the y values will stay untouched. So we're just going to take these numbers, we're going to plug them in for x. So I'm going to have 0 over 2, which is 0. 1 over 2 is a half. 4 over 2 is 2, and 9 over 2 is 4.5. Take the y values, and we're just going to repeat those. Those won't change, so we'll get 0, 1, 2, 3. That's the green graph. The blue one, let's move this over here. Okay, to get the blue one, we're going to start from the base, and we're going to move over to, this time it's going to be 2x. Okay, sorry, this is not blue, it's orange. That second one we did was orange. Get the same color here. Okay. So to get h of x, we said it was horizontally stretched by a factor of 2. So I got to multiply these x values by 2. That's what I'm writing right here. That shows a horizontal stretch by factor 2. Y will stay the same. So plug these in for x, and this right here. 2 times 0 is 0. 1 times 2 is 2. 4 times 2 is 8. 9 times 2 is 18. Okay, plug in those values for y. We're going to get 0, 1, 2, and 3. Those don't change. All right, let's get our graph. And once we get our graphs in, then we still need to state the domain and range for everything. So we'll go ahead and do that right after. So I can kind of copy the same type of axis setup. So x will still be positive. So that's our y value. The x-axis, I mean, y is positive also, so y can start over here as well. Sorry, it's our x value again. Okay, there we go. So like the axes are labeled, plot our base function 0, 1, 1, 4, 2, and 9, 3. That's f of x. G of x. We're dividing all the x values by 2. So that means I'm going to have 0, 0, a half 1, 2, 2, and 4.5, 3. Okay, you can see g of x is horizontally compressed. Okay, because my distances, so normally I have a distance of 4 here in the x, but now I get half that. This is a distance of 2. Okay, like this point here, this point has a distance of 9 to the y-axis. Now we only have a distance of 4.5. It's half that. So the scale factor is applied to x. That's why you see x is being changed in all of those. Okay, the orange one, we have 0, 0, we have 2, 1, we have 8, 2, and then we got 18, 3, which we don't have a spot for. It's going to be way out, somewhere out there. So we'll draw that like that. Okay, that's h of x. This one right here, h of x. So notice the x distance gets doubled. So here we have 4 to this point. Now that turns into a distance of 8. 1 for this one turned into a distance of 2. So the x values were multiplied. It was horizontally stretched. All right, the domain and range for all of these. So I know we should have did A in part A and then do B right now, but it's kind of funny. If you look at the graphs, notice the domain and range. They're all the same. X values start at 0 and increase this way. And for all of them, the y values start at 0 and go up to positive infinity. So with this vertical and horizontal stretch, in this case, because that's all that's been done, we're not seeing any changes with the domain and range. So our domain for all of them is x is an element of R. X is greater than and equal to 0. And the range for all of them, y is an element of R, y is greater than 0. Okay, so I'm just going to say for all functions, and A and B. Okay. All right, so that is it for this first example, and I'll see you guys in the next video.